Alright, let's get started. I'm gonna be solving another Leetcode question today. Probably, well, I did a hard one last week, which was the guess the word, and I'll do a medium today. Okay, let's see here. Actually, let me expand this. Let's do this one. This looks interesting. Top K frequent elements. Something generic like this, I feel like would be helpful because there is a lot of there are a lot of questions that are essentially just variation of this concept, which is how do you pick the top K blank? And then usually you have to do some, like, if you have a variation of this question, you'll have some special logic for that question, but at the end of the day, it might be the same thing. But let's read this real quick. So given a non-empty array of integers, return the K most frequent elements. Nums 1, 1, 1, 2, 2, 2, 3. Okay, so anytime I see a problem that talks about frequency, of course the nice solution would be to sort of do a O of n square computation where you, I don't know, you see, okay, 1, how many ones are there in the list, and then you count 3, and then you put it down somewhere in some sort of data structure. But I think this is pretty straightforward. Anytime you have to count the frequency of elements, the go-to data structure would be a hash table, or essentially a dictionary in Python. So that is how I would calculate the frequencies of the elements, and then we can figure out how can we pick the K most elements from there. Your algorithm's time complexity must be better than O of n log n. Okay, so we know that adding things to the dictionary and getting the frequencies would be O of n. So let's do that. So okay, so what should our this is what our function should look like. Def make this and then this just takes in a nums, which is and K. Okay, so what we want to do first is just get all the frequencies, right? So okay, so let's say I want a frequency table, and I call a function called get frequency, and then I pass in nums. Okay. So I'm going to be implementing this function first, which should be pretty straightforward. And then this takes in a list. And then let's just say, well, okay, so there are there are different ways to do this, right? So you could leverage something like the counter class from collections object, because that makes this thing way easier. And I can talk about it a little bit. So the traditional way of how you would do this is you would create a dictionary D, and then you can just go for num in nums D num. Okay, so there are multiple things, right? So you'll have to check if num in D So if number is already in dictionary, then dnum plus equals to 1, else dnum equals to 1. And the reason we do this if else loop is because if I don't do this, then if I just call this straight up, then it will get a key error, because the first time it encounters a number, it's not guaranteed to be in the dictionary, because the dictionary always starts out empty, right? So this is a very verbose way of doing it. And then I could just write return D. So this is when you write it like this, this kind of tells the interviewer that, okay, you know how a dictionary works, you know how to look at the edge cases. But think of instances where building this dictionary is considered a trivial portion of the problem. Maybe the problem is way more complex and you're running short of time. Then there are different ways to do it, right? So what you could do is you could, from collections, import default dict. Okay, so what does the default dict do? When you use the default dict from the collections library, you can tell it what the default value should be for any key. So what that allows you to do is that allows you to completely get rid of this check. So instead of so what happens is when you tell the default dict that the default value should be an int, you can simply do dnum plus equals to 1. And the default dict class handles the abstraction of instantiating it to a default value when necessary, and if it's not necessary, then it just increments it by 1. So you can see we saved a little bit of time, and we potentially bypassed some errors that could have happened, and the interviewer could have docked some points. But the fastest way to do this would be to import the counter class from collections, which is built for exactly something like this. So the collections module the library has a class called counter that, because counting the frequencies of things in a list is such a common in that they decided that this would be better off as one of a standard library. So what you can do is you can just call counter nums, and that does all this thing for us. So if you're running short of time, you can just, if I was in this place, I would just tell the interviewer, hey, you know what, I am going to use the counter class from the collections library, and this is why, because it allows me to save time, and this is pretty trivial. If you still want me to write it, I can do that, but if not, I think this is good enough. Okay, so cool. So this returns to me a dictionary of the frequencies of these numbers. And now we need the k-most, right? Wait, why isn't this scrolling? There you go. So we need to return the k-most frequent elements. So similar to how whenever you see frequencies, or you have to count the instances, or count how many instances of X or Y are there, you use a dictionary. Whenever you have to keep track of k most or k least things, heap is usually the best way to go, either a mean heap or a max heap. And we can talk about why that's the case. So in this case, what we can do is, I think the library for Python is called heapq. So we can use the heapq library. I wish I had made more space, but you can imagine that we can write import heapq. Usually if you need to use heap, this is the way to go. It's important to know when or why to use heap and the functions that you can use in the heapq library. If you want to use a heap to solve a problem, you don't have to implement it from scratch. At least that's been the case for me so far. So we can import the heapq, and we can talk about why this is a good idea. So what would be a naive way to see what are the k most frequent elements? You could, so they said our time complexity needs to be O of n log n, right? So we don't, to be honest, we don't necessarily need a heap, right? A naive way to do this would be O of n squared, where we check the value and then we check it against all other values and we find out what the maximum value is, and then we ignore that and we find out what the next maximum value is. But I think the more intuitive solution that would be on most people's mind is to make this, so if my frequency table looks like this, so there's 5 of, okay, so these are numbers, right? So there's, so according to our test case here, say there's 3 1s, 2 2s, and 1 3. And then what the intuitive way to do that would be to kind of write the frequencies in a table, right? In a list where there's the corresponding, we keep track of the corresponding values, the frequency. So these are the nums, and then these are the frequencies, right? And then we can just sort this. And then we get, so I guess this is already sorted, but we get 1, 2, 3, and then we know what k is, and we need the k most frequent elements. So we traverse this until we get k elements. So while I is less than k, we traverse it this way, right? So so the problem with that is, actually there's no problem with that, but that is one way to do it. So the other way to do it would be a heap, which I like better because you don't have to store, you don't have to sort all the values. So this is, the time complexity is in the order n log n, but we can do better. The way we could do that is we could keep a list of, so let's say k most, and we make this an empty list, right? And then we can say, so what is the guarantee of a heap? So generally, if I have a heap and I put in 2, 3, and 1, if I call pop, then I'll get 1, right? And then if I call pop again, I'll get 2. So what we could do is we could heapify, we could make a list of all the frequencies, and then we could not just frequencies, we could insert them as tuples, right? So our frequency table looks like this. So what we could do is we could make a list of the frequencies. So this is the frequency and this is the num. And we can say 2, 2, and then we can say 3, 1. And then we could heapify this, which heapify is always O of n, the time complexity for heapify. And then we could heap pop. So heapifying a new a list is O of n. And then when you call heap pop after that heapifying, this would, heap pop itself would be O of 1, but then heapifying again would be log of n. So what we could do is we could say that in our heap we want to store k elements only, and say we put in this, and what we want, say the value of k is 2. So we put in 3 and we say, okay, this deserves to be in here. But when we put in 2, we say, hey, is 2, is the size of my heap still less than k? If so, then just add it away. So I add it. But when I want to insert 1, I want to know what is the max value of my heap so far. Is it more than that? Sorry, no, I want to know what's the minimum value. I want to know what's the minimum value of my heap so far. If it is more than that, then cross this out and insert this into the heap. If not, then just ignore it. Does that make sense? So what we need to keep is a min heap. Okay, so let's implement this. So we do kmost, and then we can do for num and then frequency in frequency table dot items. So I can say if kmost, if length of kmost is less than k, then simply kmost, then this is when we leverage our heap queue library. We can do heap queue, heap push, it's called kmost, and the value we want to push is the frequency and then the num. And the reason we want to push the num along with this later is because what we have to return is only the elements, not their corresponding values. So else what we want to do is p is equal to, so let's say min num, actually, sorry, what I want to do is I want to pop the minimum most value right now, right? So I want to do min frequency and min num equals to heap queue heap pop from the kmost heap, right? Because this gives me a min frequency and a min number. And then I can say if num is greater than min num, then heap queue dot heap push what are we going to push? We're going to push into kmost the new frequency and number. If not, then we heap push whatever was in there already. So min frequency and then min num. Okay. And then so after this whole thing is done, I'm left with a list of frequency and numbers. So from our case, what would that look like? So we know this is what our table looks like, right? So I would say, so kmost is going to be an empty list, right? So I get 1, 3 for num frequency in frequency table dot items. Is length of kmost less than k? It is. So what I do is I simply push this thing. So I do frequency, comma, the number. Then we go on there again. And this time our pair is 2, 2. But length of kmost is still less than k because we're for our test case we're looking at k equals to 2. So we just put this in there. Now in our third iteration, what we're looking at is a pair of 3 and 1. So is length of kmost less than k? No, it's not. So else, what do? We pop the minimum frequency and minimum item, so which is this guy. We see if the, oh, there you go, that's a little bug. We're not going to compare the number, we're going to compare the frequency. Great, I'm glad I walked through this test case. So is the frequency, which is 1. Is it more than the min frequency right now, which is 2? It's not. So what do we do? We heap push whatever was in there anyway. So this goes back into the heap. So this is what KMOS looks like right now at the end of. But what we need to return is 3. What do we need to return? We need to return 1 and 2. So these two values, not the whole thing. So now I can just do a quick computation to clean that up. So I'm just gonna erase all this stuff. Okay, so just clean up all that's left is most. So over here, return. Let's see if we can do some list comprehension. K for, oh man, I haven't done this in such a long, wait. K for K and K most. I think that does what I want to do. Yeah. Okay, so we ignore the frequency and then we just take the number. Or maybe instead of calling this K, that's kind of misleading. Let's just call it N, because that's really what it is. Alright, cool. Okay, so why did we do this over doing the sort, which would have given us an O(n) log n anyway? Because let's think about it. So we know this operation takes O of n, because you actually have to go through all the numbers and figure it out. But what is the complexity, the time and space complexity of this thing, right? We know we have to go through all the numbers, so it's O of n. So this is the outer thing, operation. But for the inner operation, we only ever heap push and heap pop things from a heap that has at most k elements, right? So when you heapify this, every time you push something new in it, what is your, when you push or you pop something, your operation, the time complexity for that is log k. So